This is a discussion on uniform circular motion. We're going to take a look at things traveling in a circle, and it's particularly the forces that are required to do that. The uniform circular motion is the motion of an object traveling at a constant uniform speed in a circular path. So our object is not going to be traveling. Its speed is not going to be increasing. The direction will be changing, but the speed will not be increasing. So a good example of that is just a toy airplane where you're holding on to it, making this thing travel in a circle. And you'll notice that the velocity vector is always tangent to the circle. You see that red velocity vector pointing tangent to the circle. And if you think about it, this person is pulling in on the string, and there's something called a centripetal force that we're going to be talking about. And that's always pointed in towards the center of the circle. You'll see it pointing in right along the string, and that's called a centripetal force. It's a force pointing in towards the center, causing this plane to be moving in a circle. If that string wasn't there, that we cut the string at any point, that airplane would actually travel in a straight line, tangent to the circle, due to the inertia of that object. An object in motion in a straight line an object in motion wants to travel in a straight line. But we are causing it not to travel in a straight line by having this force in towards the center of the circle. The next thing we're going to study is the period of circular motion. The period is just the time it takes to go once around the circle. That's the definition of it. To make one complete revolution, the time does it take? The speed, which is distance divided by time, is circumference divided by the period. Our distance is 2 pi r, so our speed is, this part right here is our distance, 2 pi r, and our period is the time. So we're doing 2 pi r divided by t. So this is an equation you need to put in your in the back of your notebook under this chapter, chapter 5. Okay, so let's go ahead and take a look at an example. So we're going to do an example problem here. The wheel of a car has a radius of 0.29 meters and is being rotated at 830 revolutions per minute on a tire balancing machine. Determine the speed in meters per second at which the outer edge of the wheel is moving. So we know that when something's moving in a circle, we want to do the distance over time. And in this case here, it's going to be v equals 2 pi r over the period. Now we know what the radius is. We know it's 0.29 meters, so we can plug that in now. But the one thing stopping me from solving this problem is the period. In other words, the time to go once around the circle. Well, the other piece of information we have is this 830 revolutions per minute. Now I'm going to take a look at that here and use that to find the period. It's not set up the way I want it to be set up, though. What I want, instead of revolutions per minute, I want minutes per revolution. So I'm going to go ahead and rewrite this as minutes per revolution. So now I have 1 minute per 830 revolutions. I just inverted it, and I know in 1 minute there'll be 830 of those revolutions. So I'm going to go ahead and convert that over to seconds. So I don't want minutes, I want seconds. So I know there's 60 seconds per 1 minute, 6 seconds in a minute, so now I cancel out the minutes. And I have seconds per revolution, so I have to take 1 times 60 divided by 830, and that will tell me the seconds for each revolution, which ends up equaling 0.072 seconds per revolution. So now I can take that and plug it in for my period. I know it's 0.072 seconds to go once around, so that's my period. And now I can come up with my answer in meters per second. And I end up with my answer of 25.3 meters per second. The next term I want to take a look at is something called centripetal acceleration. Now, centripetal means center-seeking acceleration. It's an acceleration that points in towards the center while something travels in a circle. And in our problems, our speed is not changing, so we're not accelerating because we have a change in speed. We're accelerating because we have a change in direction. What's causing that change in direction is that that in that original example of the airplane is that force of that string pulling in towards the center, and that's called a centripetal force in towards the center. So centripetal acceleration is the same idea, in towards the center. The equation that we're going to use for finding centripetal acceleration is v squared over r. It's the speed of the object divided by the radius of the circle. So the speed of the object squared divided by the radius of the circle is how you calculate that centripetal acceleration. It ends up being, the units are still meters per second squared. And this needs to be written in your equation sheet in your notebook in chapter 5. And again, the direction of the centripetal acceleration is always towards the center of the circle. So here we have an object traveling in a circle, and the two vectors we've talked about so far are drawn here. The velocity vector, or actually, yeah, the velocity vector you'll see is always changing its direction. Its size always stays the same because the speed is the same. And this acceleration vector is always pointing towards the center of the circle. It's called a centripetal acceleration. So these are the two vectors we've learned so far. But also the centripetal force vector will be pointing towards the center of the circle as well. Here we have just a simple, straightforward problem. It says the bobsled track at the 1994 Olympics in Lillehammer, Norway, contained turns with a radii of 33 meters and 24 meters. Find the centripetal acceleration of each turn for a speed of 34 meters per second, a speed that was achieved in a two-minute event. Express the answers at multiples of g, 9.8 meters per second squared. So what we're going to do is we're going to actually find the answers and see how many times 9.8 will go into those answers. So it's pretty straightforward. You just go ahead and use this centripetal acceleration equation of v squared over r. And for the first circle, the radius of 33 meters, you end up with 35 meters per second squared. And what you do is you divide 9.8 into that to get an answer of 3.6 g. And then for the second one, when the radius is smaller, 24 meters, you get an answer of 48 meters per second squared for your centripetal acceleration. Divide that by 9.8, and you get 4.9 g. Now, we're going to formally talk about centripetal force. So we've talked about it already. It's that center-seeking force causing something to keep moving in a circle. It has an equation, which is mv squared over r, which is exactly the same thing as if we were to have F equals ma. In this case, it just happens to be centripetal acceleration, centripetal force. And if I plug in the v squared over r for centripetal acceleration, we get m, and then there's our v squared over r for the centripetal acceleration, and that's where the v squared over r comes from. It's just like F equals ma. And again, we see that it always points towards the center of the circle, and it always changes as the object moves. That direction always changes. The value stays the same, but the speed is constant, but its direction always changes. So here we have an example problem. The model airplane in figure 5.7 has a mass of 0.9 kilograms. It moves at a constant speed on a circle that is parallel to the ground. The path of the airplane and its guideline lay in the same horizontal plane. Because of the weight of the plane is balanced by the lift generated by its wings. Find the tension T in the guideline, which has a length of 17 meters, for speeds of 19 and 38 meters per second. So why don't you pause the video and see if you can come up with the correct answer for this. So for the 19 meters per second, we end up with an answer of 19.1 newtons. And if we have a different answer, make sure you square the velocity. That's a common mistake. And then we do the exact same thing, but instead of 19 there, we're going to put in 38. In this case here, we end up with an answer of 76.4. This last example is compare the maximum speeds at which a car can safely negotiate an unbanked turn, in other words, it's horizontal, with a radius of 50 meters in dry weather. It has a coefficient of static friction of 0.9. In icy weather, it has a coefficient of static friction of 0.1. So we're going to go ahead and take a look at this, and if you look at the front view of the car, you'll see something like this. Actually, I'm just going to use this picture over here. The force of friction is in towards the center of that circle. The force of friction from the tires is pointing in towards the center. So actually, that force of friction is your centripetal force. So what I'm going to do is plug in the equation for force of friction, which is mu times the normal force, equals the mass of the car times the velocity squared over r. And we also know, since this is a flat horizontal surface, that normal force we can plug in as weight. So now we have mu times mg equals mv squared over r. And we see that the masses cancel. We want to solve for the maximum speed. So let's go ahead and cross multiply and square root both sides. End up with a velocity of square root of mu g r. And we're just going to go ahead and plug in our values now. The first example, mu ends up equaling 0.9. G equals 10. And r will always equal 50. So in our first example, our velocity ends up equaling 21.2 meters per second. And in our second example, our mu now has become a smaller value. We're in icy conditions here. And we make our mu 0.1, much different. And let's see what the difference in the speed is to negotiate that curve safely. So in this case, the answer is much smaller, 7.1 meters per second to go around that turn.